For being here. My name is Sunny. I'm a grad student at MIT, and many thanks to the organizers for bringing us back together again. Today, I'd like to tell you about Extractors, which is a new architectural proposal for building a quantum computer based on LDPC codes instead of the more conventional surface code. This is joint work with Alex Coton, Don Williamson, and Ted Yoder. So let me start with a bit of motivation on why we would want to consider a different kind of quantum computer. It has been fairly well established in the community, I think, that surface code is the leading candidate for building a large-scale and fault-tolerant quantum computer that could one day realize the promise of factoring. Now, this advantage of surface code really comes from a lot of its amazing properties. For instance, it has high threshold, it can be implemented with 2D connectivity, and we understand how to perform decoding and logical computation with the surface code. On the other hand, we also know that surface code has a very clear limitation, which is it has a significant asymptotic space overhead. And if we want to translate this asymptotic overhead down to practice on the scale of factoring, the typically quoted number is about 1,000 physical qubit per logical qubit to operate on it. Now, of course, that number keeps decreasing with Craig Guinea's new paper and all the future works. But this rough scale and the fact that the asymptotic space overhead increases rapidly does not change with the surface code. This motivated a lot of us to consider more space-efficient approaches, more space-efficient codes, in particular these LDPC codes, which gave a theoretical promise that we can implement any large enough computation fault-tolerantly with a constant space overhead. The question I like to bring up here is, at what scale can we really realize this theoretical asymptotic promise to potentially gain a practical advantage over surface code, at least in terms of the number of qubits, in terms of space advantage? I think this is a great time to be asking this question right now, because over the past couple of years, we have seen tremendous progress in the study of LDPC codes, especially in the regime of memory. So let me define this very quickly. LDPC stands for low density parity check. It says that every stabilizer is in a constant number of qubits, and every qubit is in a constant number of stabilizers. So again, this is an asymptotic definition, but the promise of these codes is that they have better encoding rate than the surface code, being more space efficient. This promise has been fairly well realized in recent theoretical and practical constructions, so let me name a few. I'm going to use the notation NKD for physical logical qubits and distance. So there's the bivariate bicycle code by IBM, which has received a lot of attention. There's the hypergraph product code, which have those parameters, or one instance of them. There's also the lifted or balanced product codes, which have even higher encoding rate than these hypergraph product codes. And if we simply compare parameters against the surface code at the same distance, we do see that we are encoding a lot more logical information compactly into these LDPC codes. Of course, building a memory is not just about parameters. We need to talk about decoding algorithms, threshold, logical error rates, the difficulty in building hardware, all of these problems. And I think it's fair to say that we've been making great progress on all of these fronts in recent years. But the end goal with quantum computation is to actually build a computer, right? And to build a computer, we need to study this problem of not only protecting and encoded logical information, we need to figure out how to act fault-tolerantly on these encoded logical information. That's the problem of performing logical computation on LDPC codes. And it's a fairly long-standing challenge in the field, with many, many different works attacking this problem from many different directions. The purpose of this work that I'm presenting here today is to propose a new solution to bridge this gap from the memories that we are studying today to the computers that we want to design for the future. And this solution is what we call the extractor architecture. So throughout this talk, I'll go through more and more details, high level and low level, of the extractor architecture. But for now, let me make a few promises. Let me highlight a few features of our solution, and I will gradually fulfill these promises as we go on. So the first and main feature of our solution is that it's built upon this new primitive that we designed called an extractor. And the punchline here is that any quantum code, stabilizer code to be specific, can be augmented by an extractor system to become a computational block. I'll define what computation and augment mean in a second, but this is what we call an extractor-augmented computational EAC block. In short, extractors, they augment memories that we have into processors. The second feature is that given any magic state factory, specifically T-state factory based on any particular code of your choice, we can implement universal quantum computation via parallelized logical operations. The third feature is that the entire architecture, the entire system, can be implemented with fixed and constant degree connectivity. Now, of course, you can ask, we have all of these neutral atom proposals. What if my qubits can move? Is there an advantage to that? Of course, having movable qubits is very, very helpful. I'll discuss that in a bit. But it's not necessary to implement this architecture. You can do this entire architecture with a superconducting device.
What does the word processor mean here?
I would define that. I'll talk about that in a bit. And the last feature is that this architecture, the solution we propose, is very optimizable, and we have data from previous work that shows that we should get fairly practical space and time overhead with this solution. So I really made a lot of promises. I've gotten some questions already. Let me gradually fulfill all of these promises. And let me start by defining what I mean by computation and later what I mean by augment. So usually when we talk about universal computation, we talk about Clifford plus T circuits. In this talk, I'll write them slightly differently. I'll write them in terms of Pauli rotations. So in particular, a Pauli gate is a pi over 2 rotation, a Clifford is pi over 4, a T gate can be written as pi over 8, and if I write all of these rotations, I can write any universal circuit in this way. The reason behind writing them as rotation is that I can implement Pauli rotation with Pauli measurements. And here are the two circuit identities we refer to commonly. So let me explain what's going on here. This is a pi over 4 Pauli rotation with the operator P, in this case on 2 logical qubits, but it doesn't matter how many qubits there is. I can implement this pi over 4 rotation, this unitary, by introducing an ancilla qubit in the 0 state and measuring the Pauli observable P tensor X on the entire system. So when I measure this Pauli observable, there's the plus and minus 1 eigenstate. I'm going to get one of them as a classical bit. And then I'm going to measure the ancilla system with the minus y operator, again getting a plus minus 1 bit. And those two classical bits will control this pi over 2 correction, we call it a correction, later in the circuit. But the claim here is that by doing this procedure, I can implement this pi over 4 rotation with 2 logical Pauli measurements and 1 ancilla qubit. Similarly, I can do my pi over 8 rotations, which is all of my non-Clifford gates, using a T state instead of a 0 state. So this is very similar to magic state teleportation. Great. That's what we mean by computation, is this Pauli-based model of computation, where if you give me a source of magic states and a way to perform any Pauli measurements I want, I can perform universal computation for you. And if we take this to fault tolerance, we'll say fault-tolerant measurements plus magic state factory gives us universal fault-tolerant computation. This is what I mean by computation. Now, we have many proposals to study magic states. So for this talk, let me focus on how to get the other part, the fault-tolerant measurements, which Dom have talked about quite a bit in the previous talk. So let me start with the example of lattice surgery on surface code. I'll go through the high-level ideas without going through all the details as Dom have. But logical measurement on surface code can be done by lattice surgery in this procedure. Let me illustrate this. Suppose I have 2 patches of surface code with 2 logical qubits. And what I want to do is to perform a measurement of an X tensor X logical operator on these 2 logical qubits. So you will notice that this X tensor X operator is fairly large on a surface code patch that's going to be weight 2D operator. And doing it directly will be fairly challenging and not fault tolerant. The key idea here is that we'll introduce a new set of stabilizers, these red stabilizers in the middle, which will effectively merge these 2 patches into one. And the observation is that the product of these checks that I've introduced equals to the logical operator I want to measure. So by measuring these stabilizers, which are lower weight and simpler to do, I can obtain the logical measurement result. Once I've done that, I return back to my surface code, continue with my computation, and I've done the logical measurement. But the high-level idea to keep in mind here is that I started with a large measurement problem that's difficult to do. I've decomposed it into many small measurement problems that I can do easily fault-tolerantly. And that's the idea of lattice surgery. This idea can be generalized into LDPC codes or more general codes, and that's the idea of generalized code surgery, which Dom was presenting in the previous talk. This is first proposed by this paper, CKBB, Isaac is here. And over the past year, there has been potentially more than 10 papers and counting on code surgery, just developing it in all of these different directions. And many colleagues have complained to me that there has been so many recent papers, it's hard to follow up what's going on. So for that purpose, section 3.2 of the paper I'm presenting today, we try to give a 2-page high-level review of everything that has happened. Hopefully it will be a good starting point. But that's a digression, so let me talk about code surgery. The high-level idea is still the same. Suppose I start with a code Q and I start with a logical operator L that I want to measure. What we'll do is we'll introduce an ancilla system, initially initialized in a product state. So this ancilla system is just a bunch of physical qubits. Some of them are data qubits, some of them are check qubits. They're initialized into this product state. And I would perform this code deformation procedure, which is really, I'll define a new set of stabilizers, and I'll measure this new set of stabilizers. This new set of stabilizers will have the following property. A product of these new stabilizer will equal to the logical operator I'm trying to measure. So this is the same intuition as in surface code all over again. I started with a large measurement problem. I'm decomposing it into many small measurement problems. Once I've done that, I will measure out the ancilla qubits, return back to my code, and I'll have performed the logical measurement. But this is the high-level idea of code surgery. Great. So we can try to put together a computer using this kind of proposal, and we'll face a very interesting challenge, perhaps a fairly unique challenge when we talk about these more compact memories, these more space-efficient codes, which is by being more space efficient, they really have a lot of operators. They really have a lot of Pauli operators. If you look at a surface code, there's 3 non-identity Pauli operators, and I just need to figure out how to do each of the 3. But here I have many operators, and they overlap all over the place. And if I want to build, as in previous work, for every operator build an ancilla system, I'm probably building an exponential many of ancilla systems, and that's not going to work in practice or in theory. The overhead will very quickly blow up. The key technical contribution of the work that I'm presenting here today is the proposal of a new solution to the surgery problem, which is we propose this extractor system. It is a single ancilla system that is capable of measuring any logical Pauli operator on the memory or on the base code Q. And that's why we call this an extractor-augmented computational block, because with this system, it turns a memory into a processor. Great. So you should be very dubious of this claim, and you should ask many questions. The first you should ask is, how big is this system? Because if I'm building like numerous systems, merging them into one and just call it the extractor, that's not very interesting. But it turns out that for any stabilizer code on n physical qubits, I can build a LDPC extractor system of size O tilde of n. So this O tilde here hides a log cubed factor that were discussed in previous talks. We hide this here, first of all, it's a bit ugly, but also because it does not quite capture what we believe as the practical overhead of this proposal. Because we have examples from previous works which built partial extractors on, for instance, the bicycle code, which have a very small space overhead relative to what's presented in theory. And we expect this trend to continue with a lot of the works that we're doing now. So that's the first claim. The space overhead is fairly reasonable. The next claim is that any operator, Pauli operator, can be measured using D-syndrome extraction cycles. Okay? So this is a fairly standard time overhead. Of course, you want this to be O of 1. We'll discuss that a little bit at the end of the talk. But right now, this is a fairly standard time overhead. And that's why we really call this an extractor, because this one system can extract any logical Pauli observable from this memory. And I should mention that this primitive is built using tools developed in these 3 previous papers, all of which Dom has mentioned and discussed. Please pause me with any questions, but this is really the first main technical contribution of the work that I'm presenting here today. So we'll go into, right now I'll treat this as a black box, as this extractor system. Later on in the talk, I will open the box a little bit to explain how it's capable of measuring any operator you want. But for now, I would like to focus on a high-level idea of how to design a computer out of the extractor. And actually, we'll use the extractor primitive and one other primitive. This other primitive, Dom has discussed a bit, is the bridge and adapter primitive developed in these two previous works. Intuitively, it's very simple. It's just an LDPC ancilla system that can connect two extractors into a bigger extractor. So previously, I can measure any operator on a single block. Now I can measure any operator on connected blocks. So here's an example. I can connect two of these EAC blocks with a bridge. Now if I have an operator or a Pauli rotation I want to implement on these two blocks, I can do them with this augmented system. I can connect an EAC block to a source of magic state, and now I can perform not only the pi/4 rotations, but also the pi/8 rotations, and therefore universal computation with this proposal. So you might ask me, there seems to be two names for the same system that I'm giving here. Is there any difference? We give it two names just to highlight the different use cases. If it connects blocks of the same code, we call it a bridge. If it connects blocks of different codes, we call it an adapter, because it is really changing logical information stored in one medium and format into logical information stored in another medium and a different format. That's why we call it an adapter. Great, so with these two primitives, we can now put together a fairly intuitive architectural solution to build a quantum computer. And let me start by giving a minimal working example of such an architecture. And that roughly looks like this. So we've seen this already, but let me highlight a few components. On top, we'll have an NKD quantum code, preferably an LDPC code of very high rate. And it's augmented by this extractor block. This is what we call an EAC block on top. In the middle here, we have this adapter, which is connecting the extractor system to a factory. On the bottom, there's an arbitrary T-state factory that's just whatever you want. It's supplying T-states for your computation. Why do I call this a minimal working example? And what are some features I want to highlight here? First of all, every logical measurement on qubits in Q, supported potentially on magic states, can be measured in D-syndrome extraction cycles. A very standard time overhead. We will hope to get it lower, but right now it's very standard. And this minimal working example can be built with any code and any magic state factory. So for simplicity and for near-term purposes, you can consider a small LDPC code plus maybe a magic state cultivation patch. And this entire system, like I promised earlier, it has fixed and constant degree connectivity. None of my qubits needs to move. Once you build it, this entire system will work. So hopefully with the minimal working example, I have fulfilled some of the promises I made on the third slide of this talk. But we can really take this example to a much bigger architecture very intuitively and very easily. And that will look roughly as follows. So on the top, I'm going to have these EAC blocks connected by bridges. Right here, I've shown you 3 blocks connected by 2 bridges. But in principle, it can be any number of blocks connected by any number of bridges, depending on your hardware and cost constraints. Here, I have storage units for T-states, which are connected to the EAC blocks by adapters. They're there for universal computation. And at the bottom, you can have any magic state factory of your choice, potentially a centralized factory that's supplying magic state to all of these storage units. This is what a large-scale architecture looks like. And let me, again, highlight a few features. First of all, any logical Pauli operator supported on blocks and caches that are connected by these bridges and adapters, they can be measured in O of D syndrome extraction cycles with fault distance D. So if you know what fault distance is, great. If you don't know what fault distance is, it's just our claim that this procedure is fault tolerant. Okay. Great. The next thing is about parallelism. Any operator supported on disjoint blocks can be measured in parallel. What do I mean by that? Suppose I have a rotation on these 2 blocks and another rotation supported on the third block. These 2 rotations or measurements can be implemented in parallel by simply pretending that this bridge doesn't exist. So that's what we mean by parallelized operation. And the third feature is that this entire architecture is very flexible. Like I mentioned earlier, right now it's 3 blocks connected by 2 bridges, but in principle, the global architecture that you design can be tailored to your specific hardware constraint or the specific algorithm or application that you have in mind. Great, so this is the extractor architecture. And now let me move on to talk about how we want to implement an arbitrary quantum computation on this architecture. I know I promised you earlier, if we can do logical measurements, then we can do, and we have a supply of magic state, then we can do universal computation. But because the extractor is a very powerful primitive, we can actually compile our gates a lot better, such that most of the Clifford gates are now essentially free on any QLDPC code of your choice. And that's the idea I want to discuss next, this compilation idea. So I'll go, yes.
It's always really interesting so far. Just to get an intuition, will the hardware for a specific extractor need to change if you use a different code?
Yes.
Like grow or shrink the code, for example?
In principle, yes.
So what that means from like a physical perspective, just to understand, right, is like you would plan out probably like some generation, right? And then everything would be designed in. And then the next generation would also do the same thing. But with new versions of the extractors, new versions of those physical complexity.
So that's a very interesting idea. Yes, what I presented here is what I would call a general purpose quantum computer. And you can, indeed, if you have a specific constraint and your hardware cannot move, then what you would do is, indeed, you would design different versions of this for larger and larger and larger applications. But if your system is, like a neutral atom system where you really get to design the specific architecture for any specific applications, then this will be a lot different. You can specialize this to any application and initialize it at runtime, like you do in a neutral atom device.
Yeah, because it's more akin to like an FPGA for the neutral atoms.
Yes.
And then actually that also raises another question. So that means that the magic architecture actually need not be fixed, right? So the like you can do whatever you want with that, right? Then you could have this memory block all fixed and really tailored, for example. And then if you have a new distiller, if you have higher demands on your magic states, right, then that can just change as long as it adapts still. You adapt this constant, right? And you don't need to change any of that memory architecture.
Absolutely, that's a great comment. Anything here you can edit, anything here can move, anything here is flexible. Basically, whatever kind of architectural design you want to optimize for your specific applications, you can do it on this extractor architecture. Yes.
What do you expect to be the restrictions in practice on like how well connected these blocks are? Like is it like 2D connectivity or something?
So probably it's not going to be 2D connectivity. Everything here is LDPC connectivity. Any LDPC code, you can implement it by partitioning the connectivity you need into many planar layers. The number of planar layers you need is really a practical question that we need to study and optimize for specific codes.
I see. Then it's like one block of planar layer.
So for instance, in the bicycle code of IBM, they talk about how to build this memory in 2 planar layers. With an extractor, probably 2 planar layers will not work. We don't know how many planar layers will be needed. But that is, again, I'll touch on it a little bit about the practical design of these extractors, and that'll be one of them. But this one thing I'd like to highlight here is that this model of an architecture is saying that here on this one block, I may have a fairly higher connectivity need, but between these multiple blocks and these multiple storage units, which are all kind of decomposable components of this architecture, these bridges and adapter are fairly low connectivity. Like each of these is of size 2D, where D is the distance of your code. So this is fairly a modular design, and you are paying a low cost of connectivity to get this modularity. Thank you for the questions. Great. So I've told you what this architecture looked like. Let me now talk about compiling onto this architecture to remove actually most of the Clifford gates that you would care about. I will go over a slide of technical ideas. Bear with me for a second, and then I'll go through a very concrete example to discuss what this means. So this compilation will be similar to the game of surface code compilation. This is a very popular surface code architecture. It's being studied in many contexts. So suppose I have a logical circuit of Pauli rotations. As I promised you earlier, this is universal. Let's consider 3 types of gates. There is the Pauli power 8 rotations. These are the non-Clifford gates. There are the pi over 4 rotations supported within a single EAC block. We call these in-block Cliffords. There's the pi over 4 rotations supported on 2 EAC blocks connected by bridges. We call them the cross-block Cliffords. The compilation idea is simply we'll conjugate all of these in-block Clifford gates to the end of the circuit using the following circuit identity. So let me explain this. Here is a Pauli rotation of angle theta, whatever angle it is. Here is a Clifford unitary U. You can exchange the order of these two gates in the circuit by moving the U to the back of the circuit and changing this Pauli operator that you're rotating around. Okay, this is going to be U dagger PU, and U is a Clifford operation, so U dagger PU is just another Pauli, and all of this goes through. And once you do all of these conjugation, I promise you that all of these in-block Clifford gates, they will be absorbed at the end of the circuit by a round of measure out. And the type 1 and type 3 rotations that remain, we'll implement them with logical measurements. So there's a lot of, kind of technical detail in one slide. Let me illustrate with a very concrete circuit example. And that's what this circuit looks like. Suppose I have a circuit on 9 logical qubits split in 3 EAC blocks. And you will notice here there are 2 types of boxes that I'm highlighting here. There are these green boxes, which are these pi over 8 rotations. They are the T gates. There are the pi over 4 rotations that are crossing 2 blocks. That's the cross-block Clifford gates. And then there are these white boxes, if you cannot see this. There are these white boxes which are all pi over 4 rotations supported within a single block. The first step that I promised you earlier is that we'll move conjugate all of these in-block Cliffords to the end of the circuit. And that's what this circuit will look like. So you will notice that at the end of the circuit, I have round of Z measurement. This is just measuring out the computational result of my algorithm. Okay? So I move all of these pi over 4 rotations to the end of the circuit. And this conjugation will change these green boxes, the Pauli operations, the Pauli operator of these Pauli rotations on these green boxes within the block. So that's what this looks like. And the second step is that all of these in-block Cliffords, they will be absorbed by the final measurement. Because at the end, I have a round of Z measurement, and I have a Clifford circuit in front of it. Well, a Clifford circuit simply changes Paulis to other Paulis. So what I do here is simply changing these Z measurements into other Pauli measurements supported on the block. And in this way, a majority of the Clifford operations in your circuit or in your application goes away. All that remains is these cross-block pi over 4 rotations and in-block pi over 8 rotations that we'll implement with logical measurements that the extractor is capable of doing. I want to pause here to see if there are any questions about this. Yes?
Can't there be like multi-block, like pi over 4 rotations after this?
So that's a great question. I started with a circuit that only have 1 block or 2 block pi over 4 rotations. And what I conjugated through are all Cliffords that are inside the same block. So the support of these Pauli operators, they will grow, but they will not, escape from the block that they started with. And that's what this makes this, essentially free, as I'll discuss in a bit. Thank you. Yes?
Just to double check, we're doing this because it's undesirable to actually have to perform the Cliffords, right?
Well, there are many ways you can imagine a universal computer with QLDPC codes. I'll discuss actually the landscape of computation in a little bit. But in this particular architecture, because all of these measurements inside the same block has essentially the same cost theoretically, I can simply remove all of these Clifford gates without blowing up my cost too much.
Well, the reason I ask is because doing this procedure, I think, is fine, right? Like mathematically, but doesn't it also introduce the potential to reduce the parallelism?
So parallelism is a very good point about this architecture. I told you that extractor can do any measurement, but at one time it can measure only one operator on one block. And the parallelism in our architecture really comes from this multi-block approach where you can do parallel operations on different blocks. So yes, if you do all of these conjugation, you will kind of remove the parallelism in the circuit that you see here. But for an extractor architecture, we do one measurement at a time. To make it into parallel measurements in an extractor architecture, that takes more work on the surgery side. But yes, that's a good point.
Well, and I guess so that makes sense for the QEC side. I think I'm also curious, do you know if there's been more work on the compilation side? Like, my understanding was there's the risk that these become really high weight, right? They like blow up in weight, like occupy lots. So Do you think that's concerning, or do you think that just needs further study, or?
That's the point of this extractor architecture. You can blow up the weight of this Pauli operator however you want inside this one block, and we'll be able to do that measurement no problem. The same cost, similar cost theoretically as you measure a small operator, because this extractor system will take care of any operator inside the one block.
Oh, so you're saying the compilation problem becomes ensuring that those high weight operators become localized within ideally one, maybe 1 to 2, right? Those extractor blocks.
Yes, that's exactly what's happening here. Every measurement is supported within 1 or 2 blocks. I don't care how expensive the operator is within the block. It can be taken care of.
Okay, because right now you're saying that the cost model is these measurements, right, are all the same cost regardless of how.
From a theory point of view, yes.
Okay.
Great. Thank you for the questions. So let me make a few remarks, some of which the questions have touched on. The first thing here is that all of these in-block Clifford gates that I've compiled away, they're essentially free. This recovers a lot of these game of surface code ideas on surface of an architectural Pauli-based computation architectural proposal on the surface code. It's very similar. Over there, they'll also compile away a lot of these Cliffords, but now they're essentially free for us because the extractor is capable of all the measurements you want to do. And this compilation, yes, heavily relies on the fact that extractors is capable. And the bottleneck of this computation after you've done this compilation is really in the supply speed of your magic states and the number of cross-block entangling pi/4 rotations that you have. And because the bottleneck is more on the algorithmic and on the supply level, this is very optimizable for your specific applications or for your specific algorithms that you want to run, because you would design this circuit, you would compile this circuit beforehand and pick what kind of extractor architecture you want to design based on the compilation, and you can lower this bottleneck or kind of even out the magic state supply issue. There are a lot of design choices here that I'll touch on very briefly later in the talk. Great. So that's the proposal of the extractor architecture, and that's the proposal of how we want to compile. I feel like I've delayed this for a long time. I told you that the extractor can do this. I never told you how it can do this. So for the next couple minutes of the talk, let me open the box a little bit to illustrate the key idea of why a single system can measure many different operators. And once I've done that, I'll come back to the architectural problem and make some high-level remarks. Great. So a lot of this builds on the previous works that Dom has talked about, and I'll introduce this notation for this very brief purpose of explaining a very high-level idea. The notation is that of a scalable Tanner graph. So usually in a Tanner graph, I have bits and I have checks and I have connections between them. Here, I'm just going to press them together and ask you to not look too deep into the notation. So these overlapping circles, they're the physical qubits of a quantum code. These overlapping boxes, they're the stabilizers of a quantum code. I'll connect them by an edge, and I'll label that edge with a symplectic check matrix. So I hope that you would agree with me. This fully specify a quantum stabilizer code Q. So in the previous talk, Dom presented that we are going to build all of these ancilla systems from a graph. And it's the same here for this extractor. We'll build a graph and build an ancilla system out of it. So we start with a graph, and we go through a specific procedure where we introduce ancilla qubits and ancilla checks into the system. I won't go through these details. I'll put that behind a box and just say that once we design this graph, we can construct this extractor system right here, where there are some ancilla qubits and some ancilla checks from the graph with a fairly simple procedure. Right now, this ancilla system that I built here is nothing but a stabilizer state. It doesn't encode information, doesn't protect information, it's just a stabilizer state. Now I should tell you how this ancilla system can extract logical Pauli observables, and that's really kind of the design choices we made in this extractor work. So I will build fixed connections between the qubits of the code and the checks of the system, and checks of the code with the qubits of the system. So I build these fixed connections that will couple my code with this extractor system. I won't tell you how these fixed connections are built. It's kind of a lot of the technical details. But at this point, you should ask me, I've told you these fixed connections. What are the Pauli actions that we should define on these fixed connections? Because this, at the moment, is an underspecified system. And that's where the design choice comes in, because these Pauli actions will depend on the operator you want to measure. Okay? Given a specific operator you want to measure, we'll pick different Pauli actions that's supported on the fixed connections that I build. And this is why a single system can perform all the measurements we want. Great, so let me just give a few kind of conditions. Given an operator, we'll pick these symplectic matrices. One I'll put on this edge, one I'll put on this edge, and there will be two conditions that will be satisfied. First of all, this entire system, now a fully specified system, commutes. So this whole system is just a code that I can measure. Okay? A well-defined measurement code. And the second condition is that the product of these vertex checks equals to the operator I want to measure. So this goes all the way back to the lattice surgery intuition. I started with a large measurement problem that I've decomposed into many smaller measurement problems. So with these two conditions, I can measure the stabilizers for D rounds, and that'll give me the logical measurement result. Great. I promised you only a peek into the box. I won't go into many other details that you can ask me about. For instance, why is this hosting LDPC? How do you bound the space? How do you prove the fault tolerance? All of these are kind of discussed in the paper. I won't go into all of these details, but they're all proved. Great. I promised you a high-level peek. That's the high-level peek. Let me now return back to the architectural picture and the more global picture, and end with some discussions and some outlooks of about building a QLDPC quantum computer. And throughout this talk, I've told you about this extractor solution, and basically I've been trying to convince you that extractor is all you need to build a quantum computer, besides a magic state factory. But there really has been a lot of work studying LDPC computation, logical computation LDPC codes. And for the next few minutes, I would like to tell you a little bit about the landscape of all of these works, and spanning many, many different papers, and give you an idea of how the extractor solution that we proposed fit into the landscape, this very vibrant landscape. Great. So there are many different ways to compute, but the first and the kind of the most favorable way people like to perform logical computation is through these symmetry gates. So what do I mean by symmetry? That's the kind of the transversal gates, the automorphism gates, and more extensively the constant depth gates that you can perform on a quantum code that will preserve the code symmetry. That's why they call it symmetry gates. And these gates are amazing. They are low overhead. They don't introduce ancilla qubits. They're usually just a constant depth gate that is very fault tolerant and very low overhead. So we love these gates, so we want to do more of them. There's the second category of computation, which is these teleportation based, that goes all the way back to the gate teleportation idea many years ago. It basically says any gate you want to do, you can prepare either a magic state or a Clifford state, and you can teleport the gate in. And I think the homomorphic measurement gadgets and a lot of these other work fall into this teleportation based computation. The third type is these code deformation ideas, which includes the code surgery and extractors that Dom and I have presented here today. On surface code, there are other understandings, such as how to do punctures or how to do code switching. I would argue that on LDPC codes, these are not yet very well understood. I put them here with question mark, hoping that one day we'll understand them better. But this is kind of broadly speaking, the landscape of computing. And I now invite you to put together a quantum computer with this landscape, with the understanding that we have here. The first proposal of universal computation, and this is what I call the standard solution. I'm not sure if this is standardized notation, but I call this the standard solution, is the following. We'll have these QLDPC blocks. We'll do as many symmetry gates as possible. Whatever low depth gates I have on my code, I'll try to do all of them as much as possible. Whatever I don't have, let me fill in the rest with these teleportation. And I'll prepare magic state factories, I'll prepare Clifford state factories to teleporting whatever I don't have to complete a universal gate set. So this goes back to the discussion of these symmetry gates. How powerful are these symmetry gates? And because these LDPC codes are these high rate codes, they are more compact memory, it turns out that these symmetry gates have an addressability issue. What is that issue? When you do these constant depth circuits that act on the entire code space, you typically act on all the logical qubits at once instead of individual logical qubits of your choice. And while these gates are very useful, they are not very sufficient because you need to control qubits individually, universally for a general purpose computer. So I think that's one of the downside of the standard solution is that potentially you need to build multiple factories for magic states and Clifford states, and this will incur a very heavy overhead. Now, this afternoon, Chris Pattison will give a talk presenting one of these standard solutions optimized heavily in the asymptotic picture. And I'd like to point out that asymptotically, this proposal is very optimized and very good. You can get constant space overhead, you can get a logarithmic time overhead, but this goes back to the question I asked at the beginning of this talk. At what scale can we realize this asymptotic theoretical promise to gain an advantage over the surface code? And I think the standard solution is a little hard to scale in practice with our current understanding. So that's the standard solution. There is another solution that were proposed earlier when we were studying the LDPC memories, and I called this the hybrid architecture. The idea is very simple. We have these more efficient memories. Why don't we just use them as memories? Why don't we store logical information in LDPC codes, these high rate codes, and whenever I need to compute, I teleport the information out into a surface code and perform computation in the surface code. So these were the ideas that were proposed when people first started to study these memories that have good practical promises. I would argue that this is not a very favorable large-scale or asymptotic proposal because if your computation are all done in surface code, it's not clear where your advantage is going to be. It's very quickly will erase all the advantage that you try to get with LDPC code. Now, the solution that I presented here today is this extractor architecture that says that if you give me a magic state factory and I build all of these extractors, then that's all we need. There are a few advantages to it. For instance, all the in-block Cliffords are essentially free. We don't build these Clifford state factories. The entire system has fixed and LDPC connectivity. You will notice that, for instance, the standard solution needs a transversal CNOT. We don't even do a transversal CNOT. There's also downsides. For instance, you have larger decoding instances with all of these code deformation procedures. All of these measurement gadgets are kind of more expensive or medium cost, I would argue, compared to these symmetry gates. But hopefully with this talk, I've convinced you that the solution that we presented here today is fairly new and different from what we already understand on LDPC computation. And actually, in just a bit, I'll tell you how our solution can be merged with all of these automorphism or symmetry gates to significantly reduce the overhead in practice. There's one final solution I'd like to highlight. This is the solution that came from this very recent work, Malcolm et al. They proposed this family of LDPC code where all the symmetry gates can take care of any Clifford computation you want on the logical qubits. So I find this to be a very interesting solution because they really have a huge symmetry space. Unfortunately, there are a bit of downsides to it. Currently, their rate is fairly low. Usually with LDPC codes, you want close to constant rate. They have logarithmic rate. And their symmetry are no longer constant depths. If you want a complicated Clifford circuit, their symmetry actually takes O of k depths. So at the moment, I will argue that these parameters need to be improved for this to be a competitive, scalable solution. That's what I want to discuss as the landscape. And now let me tell you how our extractor solution could fit into a lot of these existing knowledge that we love a lot, including automorphism and constant depth gates, and these movable qubits on neutral atoms that people won't stop talking about because they are great. So the first slide, where does automorphism gates fit? I've told you this entire talk that extractor is all you need. But if you have automorphism gates, it actually helps a lot. These are low overhead constant depth gates that can take care of a lot of our computation. So suppose your automorphism gates can perform a subset of Clifford operations U. Okay, that's logical Clifford circuits. Then you don't really need to build this extractor that can measure all of the Pauli operators. You can actually build what we call a partial extractor that can measure operators, let's say in a set O, such as U dagger OU will span the entire logical Pauli group. So this is basically saying that we have all of these automorphism gates. How can this extractor solution be fitted inside this code with a lot of symmetry to lower the overhead of extractor while complementing the entire processor design? And now you can do computation just like a full extractor. This is very similar to the 103 qubit system that we designed on the bivariate bicycle code. That's what this system roughly looks like. On the bottom, you have the bivariate bicycle code on a torus. That's the gross code. On top, you have a partial extractor, which is this system, that is only capable of actually a small set of measurements, but when complemented with the automorphism gates, it can generate the entire Clifford group, logical Clifford group on the logical qubits. And the same applies if your code has other low overhead logical operations, Clifford or non-Clifford. A lot of these partial extractors can be built to complement your code, your memory, into a processor. The next thing I'd like to discuss is how does qubit movement help? Because we have kind of the belief that with all of these neutral atom devices, they are one of the first ones that can easily realize these LDPC codes because they have this connectivity by movement. So if your architecture can, if your qubits can move, how does that change the picture of extractor architecture? And this is what I highlighted earlier. Everything in this architecture can move. Your factories, your bridges and your adapters, your your extractors, all of these can be moved to places where you need the computation. So in some sense, with this kind of design, the space overhead of your proposal is really just bounded by the active components in your circuit. You just move all of these computational units to the memories where the computation is happening. So that's one way. Also, another way is that inside a single EAC block, if you have a moving partial extractor that can touch different physical qubits, it could function as a full extractor. So that again is talking about the space and time savings in overhead. There's another way you can use this qubit movement, is that movement makes transversal C0 very easy. You can just move these two blocks together and perform a transversal C0. And if you have this primitive, which earlier I told you we don't use, if you have it, that's great. We can do the following nice trick. The extractors is capable of measuring any operator, so it can prepare an arbitrary logical stabilizer state. What this means is that it can effectively act as a Clifford factory. And by preparing these arbitrary states, you can teleport in an arbitrary Clifford circuit in O1 online step, as long as you've used these extractors to prepare these stabilizer states offline. So this is not a single Clifford state. This is an arbitrary Clifford circuit. And this means if you have these codes that have addressable non-Clifford gates, which is a fairly new set of constructions, it's not yet very practical, or theoretically, it's not yet very LDPC. But suppose you have a code with very low overhead addressable non-Clifford gates, then you can do all of your non-Clifford gates with these low weight operations, and you can build these extractor Clifford factory to teleporting your Clifford operations, however deep the circuit is. So that's just one more fun way of using extractors. There are many other ways. This entire design is very tunable. Great, so that's how a qubit movement would help. And with all of these being said, I hope that we have described how the extractor architecture fits into our existing understanding of logical computation. Let me end my talk with some remarks on where I think are some future directions to work on for this extractor design and for designing a quantum computer. So this entire work, we've talked about this design of extractors from a completely theoretical perspective. We start by taking an expander graph, do all of these graph operations, it will blow up the cost. It's a theoretical solution that works for any code. But really, when we are in practice, we have specific code and specific memories and specific decoders that we want to use. And there's the question of designing these extractors or partial extractors on promising codes, and to reduce the cost of them with automorphism gates or with code structure. This is a very promising line of work, and there are many ideas that goes into this. There's also the question of, can you lower the asymptotic space overhead, or can you argue reasonably that there's a small constant space overhead in practice? There are also many ideas that goes into this. And finally, there's the question, for instance, as Chris pointed out, what about the hardware layout and what are the optimizations I want to do with specific kind of physical qubits? Many questions to be asked here. Now, the second thread that I would like to point out is the global architecture design for specific hardware and specific applications, because I made the pitch that this entire architecture is very tunable, it's very flexible, there's huge space for optimizations. And so if you have a specific application such as factoring, there are many design questions you can ask. What code do we choose? What block size do we choose? What is the global bridge connections? And how do I supply magic state to these blocks? All questions that we can consider. And there's also the question that I think is very interesting is to combine the extractor architecture with a specialized algorithmic gadget. Okay? So what I presented here for you is that extractor architecture, it can be used as a general purpose quantum computer. But in an actual application, there are many specialized gadgets such as QFT, such as modular arithmetic, such as the QRAM that were presented yesterday. These specialized gadgets may benefit from specialized designs, and it's a question of can we combine this general purpose quantum computer that is an extractor architecture with these specialized algorithmic gadgets to really lower the overhead as a whole. Great. So I think that's very interesting as well. Now, finally, there's the question of resource estimation. I've tried to pitch to you that this thing has practical overhead. Of course, in the end, we need to show all the numbers, and unfortunately, I don't have them just yet. We have some evidence from previous works that the resources should be reasonable in practice, but this takes a lot more work. And there's the question of, for instance, if you want to compile factoring, we now have all of these different factoring algorithms that we want to do, factoring to a concrete extractor architecture. Or maybe not yet concrete, just compiling it down to these specialized algorithmic gadgets and potentially these Pauli rotation circuits. It's very optimized, and that can be implemented on any LDPC code. That's a theoretic generality that the extractor architecture provides. So this goes into a million different questions: your hardware constraints, your architectural design, how do you design your extractors, your decoders, your time overhead, many, many different practically minded and theoretical questions that we can ask here. Great. So with that, let me end my talk with a few future remarks. At the end of this talk, I hope that I've fulfilled all the promises I made to you earlier at the start and throughout this talk. I'd like to say that the extractor architecture is really a bridge that from the LDPC memories that we're studying here today to the LDPC computers that we want to design for the future. And I think this proposal really opened a fairly exciting frontier for a lot of theoretical and practical problems to be considered. And there are a lot of challenges ahead. There's the question of doing LDPC hardware. There's a lot of work in that. There's the question of doing fast and accurate decoding and many, many more problems to be considered. But hopefully with the talk today, I've given you a little more hope and optimism about building an LDPC computer in the future. So with that, I'd like to thank my amazing collaborators once again, and thank you all for being here. If you want the slides, it's available here.
Yeah, thanks, Sunny. We already have quite a few questions. Do we have more questions? Yeah.
So it seems like the extractor, you need like at least 1 qubit per stabilizer, but like in the gross code, you only needed like 103 qubits. Like it seems like less than the number of stabilizers.
Yes, so that's the idea of a partial extractor, is that if you build a full extractor on your entire code, indeed the size is at least the code, or with the approach that we've given here. But when you have all of these automorphism gates, you can say, I just want to measure a small set of operators supported on this small set of physical qubits, and I can build a measurement system for that. And I could use all of these automorphism gates to essentially rotate my logical qubits into where my extractor is and do the measurement that way. So that's, yeah.
So do you just need like extra qubits for the stabilizers that touch the like complete set of logicals that you care about?
Yes, that would be the idea of a partial extractor. Yes.
Really nice talk. Is this also compatible with transduction, or when we think about not just doing multi-chip architectures, right?
Mm-hmm.
Adding in entanglement resources, Does this just natively plug and play, or do you need to do some work on it?
This is actually very much designed for, or when we designed this, what we very much had in mind is this modular architecture. Is to say that, at some point we'll scale to large enough chips that it starts to make sense to look at more modular designs. And if you use one of these or a couple of these EAC blocks in one chip and you have multiple chips like this, what's the connectivity you need? What's the number of entanglement you need to couple all of these chips together? And the answer given here is that you only need about 2D, number of extra qubits / checks to connect these multiple blocks together. If you want to connect them with bell pairs, you can do that.
And then do you imagine, how much overhead do you imagine from that distillation is required? Like will start to become a onerous proposition?
I have not really done any of these precise resource estimations just yet, but yes, you would need like high fidelity bell pairs or entanglement to facilitate this kind of joint measurements across multiple blocks. So it's a great question. I have not thought about it.
Any more questions? If not, let's thank Sunny again for a nice talk. We have a lunch break now until 2 p.m. and then we have a talk by Chris Patterson on constant space overhead and log time overhead fault tolerance.
Okay.